Welcome to Descriptive Statistics. Today we are going to explore a fascinating concept called univariate transformation. Imagine you have data measured in one way, like degrees Celsius, but you need to analyze it in another, like degrees Fahrenheit. How do the underlying probabilities shift when the scale changes? That is exactly what we will uncover today. Let us dive in. Now that we know our goal, let us define what a transformation actually is. In statistics, a random variable is just a rule assigning numbers to outcomes. When we apply a mathematical formula to that variable, we create a new one. For instance, changing heights from inches to centimeters. The underlying physical reality does not change, but the numbers do. Our original variable x has a specific probability density. When we transform it into a new variable y, those probabilities do not vanish, but they get stretched or squished. Our main goal is to find the exact shape of this new probability distribution. Before we jump into any complex calculus, we must first figure out where our new variable actually lives. This brings us to the concept of support. The support is simply the specific range of numbers where the variable has a chance of occurring. If we do not correctly identify the support of our new variable y, all our subsequent math will be completely wrong. To find it, we take the lowest and highest possible values of x and push them through our transformation function. For example, if x ranges from 0 to 2 and our rule is y equals 3x plus 1, our new boundaries become 1 and 7. Always determine this first. With our boundaries set, we need to check one crucial property of our mathematical rule. For our standard transformation formula to work smoothly, the function must be monotonic. This means it either strictly increases all the time or strictly decreases all the time. Think of walking on a staircase where you never take a step back down. This creates a perfect one-to-one relationship, ensuring every value of y points back to exactly one unique value of x. This allows us to find the inverse function, which is our way of walking backward from y to x. If a function goes up and then down, like a parabola, we will have to carefully slice it into monotonic pieces first. Understanding monotonicity leads us directly to our master formula for univariate transformations. This formula allows us to find the new probability density function. Let us break down every piece. First, we take our old density function, but wherever we see an x, we plug in the inverse formula. Then, we multiply by the absolute value of the derivative of that inverse function. This absolute value part is called the Jacobian. It acts as a scaling factor. If our transformation stretches the data out over a wider range, the probabilities must become less dense, so the total probability remains exactly 100%. The Jacobian perfectly calculates exactly how much to stretch or squish the density. Now that we have our master formula, let us put it into practice with a basic example. Suppose we have a metal part whose length x has a density of 2x between 0 and 1 inches. A worker measures this in a new unit, creating a variable y equal to 4x. First, we find the new support. Plugging in 0 and 1, we see y lives between 0 and 4. Next, we find the inverse function by solving for x, which gives us x equals y divided by 4. Finally, we take the derivative of this inverse with respect to y, which is simply the constant 1/4. Continuing with our example, we now plug our inverse and derivative into the master formula. We replace the x in our original density with y over 4 and multiply by the absolute value of our derivative, 1/4. Since 1/4 is positive, we can drop the absolute value bars. Multiplying the 2 into the fraction gives 2y over 4. Finally, multiplying the numerators and denominators together simplifies down to y over 8. Physically, this means the transformation stretched the support from a width of 1 to a width of 4. So the density had to adjust to ensure the total probability remains exactly 1. We have successfully used the formula, but where does it actually come from? Let us derive it. We start with the cumulative distribution function, or CDF, which tells us the accumulated probability up to a certain point. The CDF of y is the probability that y is less than or equal to little y. Since y is just a transformed x, we substitute g of x. To isolate x, we apply the inverse function to both sides. Assuming a strictly increasing function, the inequality sign stays the same. This leaves us with a beautiful relationship. The cumulative probability of y is exactly equal to the cumulative probability of x at the corresponding inverse point. Continuing our derivation, we have the CDF, but we want the probability density function. To get a PDF from a CDF, we must take the derivative with respect to y. Because we have a function inside another function, we must use the chain rule from calculus. We first take the derivative of the outside function, which gives us the original PDF. Then we multiply it by the derivative of the inside inverse function. Finally, to ensure our probability density is never negative, even if the function is decreasing, we wrap the derivative in absolute value bars. This completes our proof of the master formula. To truly grasp why this derivation works, let us look at it visually. Here, we see a small range of x values being mapped to a much larger range of y values. Think of probability as a fixed amount of clay. If you spread that clay out over a wider area in the y space, it must become thinner. The absolute derivative, the Jacobian, is the exact mathematical tool that measures this stretching. It thins out the probability density curve accordingly, ensuring that the total area under the curve always remains exactly equal to 1. We have seen how the Jacobian works for simple one-way transformations. But what happens when our function is not monotonic? Suppose our rule is y equals x squared. This is a U-shaped parabola that decreases and then increases. It breaks our one-to-one rule because a positive and negative x can give the same y. To fix this, we cannot use the basic formula directly. Instead, we must carefully slice the original support into separate pieces, where each piece is monotonic on its own. We then calculate the transformed probability density for each piece separately and simply add them all together at the end. Let us tackle a harder problem to see this in action. Suppose x represents a temperature fluctuation, uniformly distributed between -1 and 1, with a constant density of 1/2. We want the distribution of the squared fluctuation, y equals x squared. First, the support. Squaring numbers between -1 and 1 gives values between 0 and 1. Because the parabola goes down then up, we split the support at 0. Piece 1 is the negative side, giving an inverse of minus square root of y. Piece 2 is the positive side, giving an inverse of positive square root of y. Continuing with our split pieces, we need the Jacobian for both. Using the power rule, the derivative of the negative square root becomes negative 1 over 2 root y. The derivative of the positive square root is positive 1 over 2 root y. Because our function was split, our master formula expands. We take the density from the left side using its specific Jacobian and add it to the density from the right side using its Jacobian. Since our original density was just the constant 1/2 everywhere, we plug that in for both terms, along with our two derivatives. For our final steps, we apply the absolute value bars, which removes the negative sign from the first derivative. This makes both terms identical and positive. Multiplying the fractions together gives 1 over 4 root y for both pieces. Since they have the same denominator, we simply add the numerators to get 2 over 4 root y, which simplifies down to our final answer, 1 over 2 root y. Physically, this massive spike near 0 happens because the slope of x squared is very flat near 0, squishing a large range of x values into a tiny range of y values. We have covered a lot of ground today. Let us review the key takeaways. First, univariate transformations are essential for translating probabilities across different mathematical scales, like moving from radius to area. Second, always remember to determine your new support boundaries before doing any calculus. Third, the Jacobian is your scaling factor. It ensures your total probability remains exactly 100% by adjusting the density. Finally, if you encounter a non-monotonic function, simply split it into monotonic pieces and add their probabilities together. You now have the tools to fluidly transform any single random variable you encounter.